Okay, good morning all. Good morning all. Am I audible? Is my voice is audible? Okay. So kindly mark your attendance using 3 parameters in the chat box. So this is the video lecture on design and analysis of algorithms. So we are currently discussing the last chapter of the module 5. So NP-complete and NP-hard problems. So in that we have gone through basic concepts, non-deterministic algorithms in yesterday's class. So in today's class, we are going to discuss the last topic, P, NP, NP-complete and NP-hard classes. P and NP. So what is P and what is NP? So NP stands for non-deterministic polynomial time. Okay, so NP means non-deterministic polynomial time. So in that P, so P is set of all decision problems solvable by deterministic algorithm. So in yesterday class, we have seen what is deterministic and what is non-deterministic. So we shall have a brief overview of that. Deterministic. So come for the word deterministic computer, where result of every operation is uniquely defined. So result of any operation is defined, then we call it as deterministic. So whereas the result is not uniquely defined, so that we call it as non-deterministic. So whose result is find, so that particular algorithms we call it as deterministic. So if the result is not being unique or result cannot be found, so then that is called as a non-deterministic algorithm. So in that, now you come for this. So P is set of decision problems solved by deterministic algorithm. So NP means set of decision problems solvable by non-deterministic. P is deterministic, NP means non-deterministic algorithm in polynomial time. So most of the P means there is a unique solution. Now NP means, so there is no unique solutions. Okay, so if each deterministic algorithm, we have seen so many algorithms, greedy algorithms. Next, we have gone with dynamic programming. Next, backtracking. All this, if each algorithm is finding the same solution for a problem, then that is called as a same solution, unique solution. If it is finding for a problem, we call it as P. So if each algorithm will give different results, that means they are not unique. So that one we call it, for that one we call it as non-deterministic. Understood? So that's why most of the problems will come under deterministic, because all problems can be solved using deterministic algorithms. So so much NP are there, complete this one is NP. So in that something or P. Okay, this implies P is a subset of NP. So keep in your mind, P is a subset of NP. The problems known to be in P are trivially in NP. So if the problems are found to be, which are the deterministic algorithm solutions, so every solutions will be inside NP only. So I am telling it's the entire NP. So inside NP you are finding some P. Okay, so now you come for the P concept. So P is the complexity class that represents the set of all distant problems that can be solved in polynomial type. So that is given instance of a problem. So decision problem. In yesterday we have gone with two types of problem. One is the decision problem. The other one is the first one is decision. Second one is optimizable. So decision problem means it will be in terms of yes and no. So non-optimizable means so you are getting a solution for that one. So that one we call it as non-optimizable. So now you come for P. P is a set of all decision problems. So it's a set of all decision problems that can be solved in P time, polynomial time. That is, given instance, the answer yes or no can be decided in polynomial time. So what are the examples you are getting? So given a connected graph G, can its vertices be colored using two colors so that no edge is monochromatic? So monochromatic means same color, no two edge, no edge. So vertices be colored using two colors. So for one edge, how many vertices you will be having? So for one edge, you will be having two vertices. So okay, so two vertices should not use same color. So that is the yes, we can color or yes, we cannot color. So that can be the decision answer for that particular question. So algorithm start with the, so given this is the problem, so you have to answer using P. Okay, so what is the problem? Given a connected graph G, can its vertices be colored using two colors so that no edge is monochromatic? Okay, so algorithm start with arbitrary vertex, color it red, and all of its neighbors blue and continue. So which is the arbitrary vertex? You color it red. Okay, and all its neighbors blue and continue. So stop when you run out of vertices or you are forced to make an edge of same color. So that is the concept. Now you come for the NP. So what is NP? The problems that can be solved through non-deterministic algorithms. So that is called as a NP problems. So NP is the complexity class that represents set of all decision problems for which the instances where the answer is yes. If we are given the answer as yes, so has proof. So if you tell yes, there should be a proof. So if you are telling yes, give the answer how you are getting that particular thing. So answer is yes, have proofs that can be verified in polynomial time. This means that if someone gives us an instance of problem and a certificate to answer being yes, we can check it that it is correct in polynomial time. So now you come for the NP examples. Okay, so NP means if a decision can be made through non-deterministic, so that is either it can be yes or it can be no. If it is yes, give the proof. Okay, so NP example, so integer factorization is in NP. So this is a problem that given integers n and m, is there an integer f with 1 less than f less than m such that f divides n. So f is a small factor of n. So this is the addition problem because the answers are yes or no. Okay. So if someone answers an instance of a problem, so the hand has integers n and m and integer f and claim that f is a factor of n. We can check the answer by performing the division n by f. So now you come for the two parts, P, NP. So, but there are some problems which are known to be in NP, but don't know if there are in P. Okay, so some problems are there that is known to be, we know it is in NP, but we don't know whether it is in P or not. So NP means, so P means there is a unique solution. Okay. So that we consider it as P and NP. Okay. So now you have to check, there are some problems which are known to be in NP, but not known if there are in P. So example is the travel decision problem version of traveling salesman problem. So it's not known whether decision TSP, traveling salesman problem, is in P. So now you have to check, is there any unique solution? Okay, unique solution should be there using all algorithms. It's not known whether the decision TSP is in P. There is no known polytime solution, but there is no proof that the solution does not exist. The most famous unsolved problem in computer science is whether P is equal to NP or P not equal to NP. So this is the most famous unsolved problem in computer science we have. So we need to check whether P is same as NP or P is not same as, that is not equal to NP. So now you come for the, that is up to P and NP. So now you come for the next thing, NP complete. So what is NP complete? Reducible problems. So given decision problems P and Q, if an algorithm can transform a solution for P into the solution for Q in polynomial time, it's said that Q is polytime reducible to P. Okay. So what we can tell? So given a decision problem P and Q, if an algorithm can transform a solution for P into solution for Q. So in polynomial, it is said that Q is polytime reducible to P. Understand carefully. So this is the reducible problem. So you have to understand carefully this one. There are given decision problems P and Q. Okay. So if an algorithm can transform a solution for P into solution for Q, transform a solution for P into solution for Q in polynomial time, it is said that Q is polytime reducible. Okay. So that is definition. So decision problem D is said to be in NP complete if it belongs to, class NP, and every problem in NP is polynomially reducible to D. Every problem in NP is polynomially reduced to D. So NP complete is a complexity class. So NP complete is a complexity class which represents set of all problems X for which it is possible to reduce any other NP problem Y to X in polynomial time. Okay. So initially this means we can solve Y quickly if we know how to solve X quickly. This means we can solve Y quickly if we know how to solve X quickly. Precisely, Y is reducible to X if there is a polynomial time algorithm F. Polynomial time algorithm F to transform the instance Y to instance X. So if your answer to Y is yes, if and only if the answer to F of Y is yes. Okay, so now you come for the NP complete. Informally, these are the hardest problems in the class NP. So if any NP complete problems can be solved by the polynomial time, then polynomial time deterministic algorithm, then every problem in NP can be solved by the polynomial time deterministic algorithm. So understand carefully, if any NP complete problem can be solved by the polynomial time deterministic algorithm, so then every problem of NP can be solved by the polynomial time deterministic algorithm. But till date, no polynomial time deterministic algorithm is known to solve any of them. So example for NP complete is CNF satisfiability problem. So CNF satisfiability problem deals with a Boolean expressions. So it is given by Cook in 1971. So CNF satisfiability problem asks whether or not one can assign values true and false to the variables of given Boolean expression in its CNF form to make the entire expression true. So coming for the examples for NP complete. So till now we have seen so many examples in DA language. So in that, in today's class, we see which are the problems which come under P, which come under NP, which come under NP complete. So example, so whatever the problems for NP complete, everything will be for NP also. So you have three cases. First one is P, second one is NP, third one is NP complete, and NP hard also there. But before you go for hard, let's see. So whatever the problems for NP complete, everything will be there for NP. Okay. So in that, I can't tell whether all NP problems can be P. Okay. So all NP problems cannot be P. So that's why, which are the examples we can take for NP complete? Traveling salesman problem. What is a traveling salesman problem we have? So that means start with a source, visit all nearby cities, and end the tour with the same starting place. So that is the concept we have. So first one is start with a starting place. So next you go visit all the nearby cities, and then you come for the end with a starting place. So that is the traveling salesman problem. So similarly, we have Hamiltonian cycle problem, click problem, subset sum problem, Boolean satisfiability problem, and many thousands of computational problems in computer science, mathematics, economics, communications will come under NP complete problems only. So NP hard problems. So these problems need not have any bound on their running time. So these problems do not have any bound. Okay, so now you are under last case. So P, NP, NP complete, NP hard. So now we are under NP hard. So these problems need not have any bound on the running time. So if any NP complete problems is polynomial time reducible to problem X, that problem X belongs to NP hard class. All NP complete problems are also NP hard. In other words, if a NP hard problem is non-deterministic polynomial time solvable, it is NP complete problem. So example of NP complete that is not NP complete is example of the NP problem that is not NPC. So that means NP problem which is not NP complete is halting problem. So this is the thing what we can tell for NP hard. So here the entire thing it is called NP. So NP, so small part we call it as P. So now you come for the hard. So this is the complete NP hard. This one is complete NP. So inside MP you are having P. Okay. So this is MP hard. So part which is a part of the, so it is the intersection of NP hard and NP. So intersection of NP hard and NP will give you NP complete. So commonly believed relationship between P, NP, NP complete and NP hard. So what we tell, the intersection of NP as well as NP hard and NP, we call it as NP complete. Understood. So now you come for the NP hard problems. If a NP-hard problem can be solved in polynomial time, then all NP-complete can be solved in polynomial. So keep in your mind, as you are getting the intersection, if NP-hard problems can be solved in polynomial time, and NP-complete can also be solved in a polynomial time. All NP-complete problems are NP-hard. Okay, as you all know, so NP-hard is derived from NP only. So that's why NP-complete problems are NP-hard, but not all NP-hard problems are not NP-complete. So NP-complete problems are a subclass of NP-hard. So NP-complete problems are the subset of NP-hard. The more conventional optimization version of TSP for finding the shortest route is NP-hard, not strictly NP-complete. So now you come for the next thing. These problems that are at least as hard as NP-complete problems. Note that NP-hard problems do not have to be in NP and they do not have to be in decision problems. The precise definition here is that problem X is NP-hard if there is a NP-complete problem Y such that Y is reducible to X in polynomial. But since any NP-complete problem can be reduced to any other NP-complete problem, so all NP-complete can be reduced to NP-hard. Therefore, if there is a solution to NP-hard problem, there is a solution to all NP problems. So NP-hard. So halting problem is a NP-hard problem. This is the problem that given a program P and the input I will let halt. Okay, so now we come under the halting problem. So what is the halting problem? So halting problem is a NP-hard problem. This is the program that given a program P and input I will let halt. So this is the decision problem, but it is not in NP. So it is clear. So it is clear that any NP complete problem can be reduced to this one. So that can be reduced to this one. As any other example, any NP complete problem is NP hard. So that marks the end of this particular thing. So actually, no, so this will be the not the end, but it's the beginning. The same halting problem what we are discussing in DA, that will be the continuation in the next some subject, automata theory and computability. So you for the fifth sem you will be having this particular problem to be solved. So it's how to solve this P, NP, NP complete and NP hard problems. Okay. So that is up to, that's why we tell this particular subject in order to solve this particular problem. So we are going to have this is not the end. So, but it is the beginning. Okay. So this is up to today's class. That is, we have gone with our concepts. So like we have discussed P, NP, NP complete and NP hard problems. So this is up to module 5. It completes the completion of module 5. So I hope you all have understood this particular concept. So I have given all the materials, lecture notes in the Google Classroom. So kindly go through the link. So submit the assignments within the specified date. So this will complete the module 5. Okay, so kindly go through all the concepts using my YouTube channel 1DPMK. Kindly like, share, subscribe for the channel and get the knowledge of the design and analysis of algorithms. Okay, so here I will be ending this particular class. So thank you all. So stay home, stay safe.